Hey guys, welcome back. Today we're going to be doing more simulation nodes and we're going to be making sure we can understand adding up velocity vectors to have attraction and push and pull vectors. The first thing we need to do is we need to make some extra objects to have inside a collection as push and pull. New collection, let's say push, and let's just say pull. Now we have our two collections of objects, and this center one we can call simulation zone. Let's go into geometry nodes, make a new system, and we're going to call this push pull points. So this is going to be a lot of nodes, and we're talking a little bit about vectors and vector math to make sure we all understand this. So the first thing we want to do, we'll do a simulation zone. Cube goes away because there's no more input geometry, and we're going to put points. And let's just do 20 starting out. So we now see 20 points right there, all in the exact same spot. And just to make it super straightforward right now, let's just have them go to the left. So we're going to do a set position, and then we're going to add an offset. And maybe I guessed right, of 0.1. It might be this way, we'll see. Let's push play. And it's going to the right. So minus 0.1. Now it's going to the left. Fantastic. I'm going to do my start frame on 0, and just do 60 frames to make it super quick to see. When it comes to simulation zones, it can get a bit confusing, but essentially all we need to do is just make sure we have really clean naming and make sure we know what we're doing. So at the very end, we're going to have the set position. So I'm going to move the set position all the way to the right, and we're going to do a bunch of math on the left and pipe it in. So for the final thing, let's just make the initial vector make sense. So let's kind of work backwards to the front. It'll make more sense as we see it. Let's do a capture or store named attribute. And let's call this V for the velocity and say final. And we'll make this a vector. And let's just say minus 0.1. And then over here, we're going to do a named attribute. We're going to do a vector. And we're going to say V final. We're going to pop this in. It's going to behave exactly as we saw before. So it's calling this vector, or this value, this vector right here, and popping it in. Now we have this. We can move this all the way to the right. Don't have to worry about it. So now the main question is, how are we going to make essentially this point move in respect to these two different collections? So first we got to pull these collections in, make it relative. So all of their different spots are relatively different in the space rather than all on the origin. And we're going to do separate children as well. This actually doesn't matter because we're going to be doing realizing instances for both of them. We have this, we have this. Fantastic. From the last tutorial, when we did simulation zones, we were able to get a direction vector by basically taking the 2 points and finding the difference. So let's just kind of like draw it out really quick. So let's say we have a point here and a point here, right? Now let's say it's an XY coordinate system. We're all familiar with this. And let's say this is 1, 1, and I almost drew it linearly. Let's pretend it's not. So let's say this is 5, 2. Who knows? Okay. So if we want to get this vector for the point from going to here, this is also just going to be, x2 minus x1, y2 minus y1, right? So then that would be 4, 1. We go over 4. So right here is 4, and we go up 1. So let's just start with the pulling, the attractors. This is the attractors right here because this says pull. We have the point data right in here. We will have to get the positional data, both of them, to subtract them because those points are positional data. So we're going to use the position attribute, and we're going to do a capture attribute of the point and the position. We have it right here. Perfect. And then what we're going to do, maybe even better, to do a store named attribute to make it really clean. Let's just call P for point and then say position. And there we go. There we go. Delete. Piping it through. So now to deal with this, we need to do a sample nearest surface. This is a newer node that didn't exist in other versions of Blender, but it does exist in 4.4. This basically will take all of the surface data of the mesh and find either the nearest point regardless of the edge or the point or the face. So this is going to be a better solution than just doing geometry proximity. And then the value we're going to use is position. And then the sample position is going to be named attribute, P position, Control C, Control V, pasting it in. Perfect. So we now have this output position of the secondary point, that positional vector. So then we're going to do a vector math. We're going to subtract the P position minus this. Then if we just plug this in and we add a normalized node right before it, normalize, let's see what happens. Maybe it's opposite. Let's do Alt S to flip these. There we go. Now it's attracting to one of the icospheres. So it's going to be the pull objects geometry, like their positional data, minus the point positional data to get that vector to look correct. Fantastic. We have this now. Now we basically need to do the exact same thing, but for this guy right here. So we have this. We can do Shift D to duplicate it. And then we can just say this should be push. And we do Alt S. And that should push it away. So now what we have is we have two normalized vectors that we can use to add together. So we have one pulling and one pushing. With these two, we literally can just do a vector math and add them together. And then this should have it calculate off of everything where the points should go. So let's just see. It's gonna go there. Okay. Now if we push this in front of it, it should be pushing maybe down here instead. Let's see. Well, it's still going. It's going to, I guess, the centroid of all of these different vectors, and that's why it's happening that way. So actually, if we move these around, it'll probably actually shift the point, depending. It's looking for the centroid of all of the different vectors being added together. So the next thing we need to do, a couple things. We need to add some noise, and we also need to add magnitude or a way to reduce this push vector depending on how close the point is. We want it to kind of almost have like a field around it. So right now, regardless of distance, these points are going to be impacted by that. So let's first just add the noise. It'll be easier to see. So inside this, we're going to want to add noise. Let's call this V push pull. And let's just do V push pull, plug it in there. And then just to make it really clean, let's also just do some groups. Select, Control G, tab out. And this is the pull system. And then we can grab this, Control G, push system, cleans it up, looks a lot more understandable. And we have it being added together. We know it's being normalized too. Awesome. So now let's add in the noise. So we have the push pull right here. Always go back and change it up. So let's add some noise. Let's just say V noise. And then we can add the noise by doing random value. We want to do a vector. We want it to be going into here. Say -1 to 1. Let's mix these together. So we're going to have V noise, mix node, vector. Now we can mix these two in like so, and let's see what happens. They're flying all around. Cool. So if we have it all the way on one, it's gonna just be the noise going everywhere. All the way on the other one, it's gonna be just those forces keeping it all together. We keep it somewhere in the middle like this, and then it's gonna be kind of all over the place looking for a solution. We now have some noise in the final. Now let's go back and into the pushing group, and let's make sure we are able to also take into account the geometry proximity of everything. So geo proximity, probably inside the actual group. And we want it to be this. This is the sample position. This is the distance, which will be the output. So we now have the distance typed out here. And we can add this together to make sure that it will scale depending on how close things are. So again, the distance, we know if it's really close, it's like 0.0001. It's really far away. It's like 10. So how do we make this number small and this number big? Just do 1 over it. We don't want it to completely explode, so we'll map range it as well. So we will do a math node here. We'll do a divide 1 over this. We're going to do a vector math to scale it. Put in scale. There. Now let's see what happens. If we do, I guess, let's change it to be more like this. Nice. So it's now kind of staying better. We move this around. And it kind of wants to move around. Oh, whoops, this is why. There we go. Now it should be better. So if we move these around, the points will move to one of the attractors depending on all of these things. But see how this field is a little too much? Like, this is too much space for me. The way we can do this is by going back into the GeoNode group. And again, making sure the realized instance geometry is where it's going, into the geometry here. Then we're going to do a map range. Map range. We know it's now going to be a big number. So let's say from like 0 to 3. And then from here, we can change this range to make it a different number depending. But I think actually in the wireframe mode, we're going to see points actually fully inside. We can add a reflect vector as well to bounce it off. I think we might do it next time. Okay, so this is going in. We have the push-pull. We have the noise. We're adding the push-pull and the noise together with a mix. We're putting it inside the final, and the final's going through. It's moving a little fast, so maybe we can add a scale and scale it by like 0.2. A bit slower now. And actually what we can do here is also normalize it again. We add it together, and then we normalize. Let's add an extra points to constantly be generated each time. So we're going to do a join geometry, and each frame should have new points coming in. Nice. And then we have points kind of coming through. And as we actually move this, it will actually have the points go to different objects depending on where it is. Nice. So I'll just do 0.3 for now. Now let's kind of figure out a cool effect we can have. So now we have the math all working. We know we have the push and the pull. So the icospheres are the pulls. What if we made like a little like maze for it? Let's see if we can get the particles to actually go through and like find the objects we care about. I'll probably just cut to where I have the maze kind of figured out. And actually it is just going through. So I think what I want to do is I want to do the reflection vector like I was talking about before. So we are actually going to do it really quick. We have the noise right here. We have this final, and then we got to add in again the reflect. We have this going, pushing, pulling, and the reflect will be a switch node off of it. And we're going to use a Raycast for the reflect. So the target geometry is going to be all of this stuff, the push and the pull. So push, pull, relative for both. And we're going to do a join geometry. And then we're going to do a realize instances. So now it's real geometry, and that's getting piped in. So what a Raycast node is going to do is it's going to take whatever we want for the target things, the ray sources. Let's say we have all these points. We want to fire rays in a specific direction and see if it hits or collides with something. We can use that is hit or is normal. So we have all this sea of points. We also have the velocities, which we know from right here, the V final. So the V final is going to be which direction these points are going to go into, which we can use for the ray direction. The source position is just the position of those points at this time. Then we know that, then we can see if these rays are going to collide with something. And we can use it as these, push and pull objects as things we don't want it to collide with. These are all the colliders. So now let's make it happen. We have our collision objects in. The source position is just going to be P position. So I'll pull this in, and we'll say P underscore position, perfect, is the source. And the ray direction is actually going to be v final, because that is direction those points are going to move in the next frame. And the ray length we can take by just doing a vector math distance. Not distance, vector math length. Nice. So now we have it all going in. And I guess the attribute we care about, does it matter? I don't think it matters actually. So all we really care about is the hit normal and the hit position if we cared about it. Mostly just the hit normal. So now to do the reflect, we can use a vector math node again. We go into here, we can do reflect, but essentially it's going to be the hit normal, and it's going to be back to the vector final. So a reflect node does something like this. We have a surface, we have a ray coming in, say it bounces here, we're expecting it to reflect like this. Why is that? Because this surface has a normal going like this, or a perpendicular reflection axis, essentially. So this is the direction of the axis of reflection, which is going to be this, and we have it bouncing there. So if we have the hit normal of whatever the geometry is, we'll be able to find that and use it to reflect the vector going in that direction. That's how it's going to work, and that's how it should work. So that's all of this right here. And I think what I will do is I will then put it in another store named attributes. It's really clean. And let's say v reflect. I think technically it should be after this because of how it's being calculated. V reflect. Got all this guy. Got all this. And then the final attribute. So this probably shouldn't be called v final. Probably we should call this instead is not v final. We probably should call it. No, I'll change it really quick. It should not be v final. This should be like v noise plus or noise push pull. So Control C. Noise push pull. Nice. That's been changed. And we can actually put this all in a group. Control G. Now a group. All cleaned up. Isn't that nice? So then this should be store named attribute v final. So this should be v push pull. We actually need a switch node. Which I guess we need this now. Is hit. Piping it out. Perfect. So if it's true, we want it to be doing v reflect. We should do. Here we go. Control C, Control V. So if this is true, we want it to be v reflect. If it's false, we want it to just be this noise. Pipe this into the final. And let's see if this actually has a bouncing now. Is it bouncing? Looking like no. So let's flip this here. Alt S. Now let's see. There we go. We're getting those bounces. It's bouncing off those collisions, and it's looking to find that object. Okay. So now let me just tinker a little bit longer to see if I can figure out how to clean this up. Yeah, look, now we have the little attractor. We can actually kind of sneak them over. We can grab them right here and kind of pull them in, stay kind of close enough so we can find their way home.
Augury.